The problems we've been working on up until this point have been from section 8.4, which is testing a claim about a mean. These tests have been performed using traditional method of comparing the test statistic to a critical value. Now I want to show you the two other methods to use with hypothesis tests: p-values and confidence intervals. So before we talk about p-values approach to the testing hypotheses, I want to work through the next few slides that'll help us learn how to state our null hypothesis and our alternate hypothesis. So I claim that the mean weight of all statistics students is at least 120 pounds. So at least means greater than or equal to. And since equals in the phrase, the claim must be that the null is usually written as null greater than or equal to, but it's okay for us only to use the equal sign, okay? But the alternate's still going to contain a less than. So this is when we use the equal sign. So I have my null hypothesis equals 120, and my mean is less than 120. So at least, that means we're saying it could be more. In this next example, I claim that the mean height of all statistics students is no more than 72 inches, okay? So my null hypothesis is going to be that my mean height is 72 inches, right? It's equal to the claim, okay? And for our other one, we're going to have the mean height is greater than 72 inches. That should be a greater than. And last but not least, I claim that the mean of all IQ of all stat students is greater than 115. So my null hypothesis is that it's going to be equal to 115. And my alternate hypothesis will be that the mean is greater than 115. So this is how we set up our null hypothesis and our alternate hypothesis. It's good to practice these. Before we start talking about a fourth example, so I claim the mean number of hours stat students work at a paying job per week equals 25, okay? Now this one, it doesn't have a greater than, it doesn't have an equal to, so we're gonna use, this should have been a 25. So we're gonna use a not equals to for my alternate hypothesis. All right, one more example. I claim that the mean number of Ted Drewes ice cream cones that stat students eat per month is not equal to 15. Okay? So the claim has not equal to in it. So since the claim does not contain any form of equality, the claim is the alternate hypothesis. And the null hypothesis is the opposite of the alternate hypothesis, so it's going to maintain an equal sign. So I have mean is 15 ice cream cones, and my alternate's that it's not equal to 15. This is my claim. And this is no difference from the claim. This is our last example. So I claim that the mean number of hours stat students spend watching TV in a given week is less than 5 hours. So less than, we're going to have our alternate hypothesis contain the less than symbol. So my null hypothesis is that there's no difference from the claimed value, so the mean is 5 hours. And my alternate hypothesis would be that the mean is less than 5 hours. Now, p-values. P-values are going to be the probability of our event occurring. So before we go any further, let me tell you when you're going to reject the null hypothesis using a p-value approach. Okay? First thing we're going to do is learn how to compute a p-value. And if this p-value is less than our alpha, then we're going to reject the null. Okay? This is the technique we used for Jill back in our first video. Only we did not agree on a significance level before we started. So our probability is going to be the area under a normal curve left by our test statistic, or z-score in most cases, sometimes a t-score. So now we have two ways to reject the null hypothesis. We can, if it lies in, we can reject it if it lies in the critical region, okay? Or if the p-value is less than the alpha. So p-values, they'll work the same way as the traditional method, both yes and no, okay? You're gonna state your null hypothesis and your alternate hypothesis. You're gonna state the alpha level, but you do not calculate any critical values. So I'm going to reject my H naught after I compute my p-value. If my p-value, so the probability of event occurring, is less than my alpha, then we reject our H naught. So some people say if p is low, reject HO. I'm pretty sure I know someone who has that on a t-shirt. Okay, so how do we compute the p-value? Well, it depends on the type of test we're making. So for a right-tailed t-test, the p-value is the area to the right of a test statistic. That was a little too big. It's the area to the right of our test statistic, so it'd be the area over here. For our left-tailed test, it'd be the area to the left of the test statistic. And for our two-tailed, it'd be the area 2 times of whatever our test statistic is. Okay, so this is what our graphs are going to look like if we were going to roughly sketch them out, which I recommend. So let's go through our sample. So a New York Times article noted that the mean lifespan for conductors, hey, this seems familiar, for 35 male conductors, that's our sample size, was 73.4 years. So this is our sample mean. In contrast to the mean of 69.5 years for all males. So this is our population mean. Assuming our population standard deviation is 8.7, we're going to use a 0.05 significance level to test the claim that male symphony conductors have a mean lifespan that is different from 69.5 years. So my null hypothesis is that our sample population is equal to the population mean. And my alternate hypothesis is going to be that it is different. I'm not told greater than or less than, so it's just going to be not equal to 69.5 years. So again, my sample size is 35, my sample mean is 73.4. We find our standard deviation, we find our alpha that's given to us, and we state our null and our alternate hypothesis. That's our first step. Next, we calculate a test statistic. Since we know our standard deviation, we're going to use a z-test. So again, I go and calculate my sample mean minus our population mean over our standard deviation over the square root of n, and I get a z-score of 2.65. So that means that our sample mean of 73.4 had a real population mean of 69.5, and we're 2.65 standard deviations above the mean. So I'm trying to find the area over here. Now when I look up 2.65, when I look 2.65 up in our Z table, right, I find that the area is 0.996, but this is the area to the left. And I'm not interested in this area. I'm interested in the area over here. So I'm going to take 1 minus 0.9960. That's going to give me an area of 0.004. So that's the area right here. Okay? But this is a two-tailed t-test. So I'm going to multiply this area by 2 to get me 0.008. This is my p-value. Because my p-value is less than our alpha, which is 0.05, we reject our H naught. So let's try this again. The effectiveness of a test prep course was studied for a random sample of 75 subjects who took the SAT before and after coaching. So this is my sample size. The difference between the scores of these 75 folks resulted in a mean increase of 0.6. We're going to assume a standard deviation of 3.8 at the 0.05 significance level, and we're going to test the claim that the population mean increase is greater than 0, indicating the course is effective in raising course. So should people take the course is what we're asking. So we have our sample size, which is 75. Sample mean is that it raised the scores 0.26. Standard deviation of test scores is 3.8, and our significance level. Now, we're looking for an improvement of a number of percentage points, right? So this, when I have mean equals 0, this is the test. The extra course has no help. And here is our claim that if you take this course, then your grade increase is going to be greater than 0. So we compute our test statistic, okay? We know that we're looking at it to be greater than 0, so this is a right-tailed t-test. I have my z-score here. That means it went up 1.3675 standard deviations. So I need to look this up in a z-table in order to get the area, over here. So let's do that. So I go to my z-table and I find a z-score of 0.9147. So the area to the left of our given value is 0.9147. So I need to take 1 minus 0.947, and that gives me the area over here, which is 0.08. Let's just round that. Now, because this is a right-tailed test, we want the area to the right of our test statistic, but 0.08 is not less than 0.05, so we've failed to reject the null hypothesis. And therefore, that means this test prep course does not seem to be effective. So it's important to note that we're tying this all back to the normal curve. Okay, normal curves are really important. So if you aren't feeling super confident about calculating z-scores, that might be something to go back and review.